Okay, well, thank you very much for inviting me. So today I'd like to give you a little bit of an overview on some work that my students and I have done over the last few years that tries to gather together some ideas from signal processing, image processing, computer vision, and machine learning in order to do the kinds of things that we've been doing, which is to say develop computational imaging, computational photography algorithms. So if you look across the literature, what you'll see is a tremendous number of different kinds of filter with different names that have been introduced. And frankly, if you're a student just starting off, it can be very confusing. What do these filters all have to do with each other? How do they relate to each other? And if you want to make a contribution, where do you start? Is there a common basis to the development of a lot of these techniques? So this was kind of the point of departure for me, to try to understand some of the basic principles behind the design of some of these filters. How do they relate to each other, and how do we generalize from that going forward? So the basic way in which I like to think about the core problems in image processing is that at the root of it, you have an input image and an output image, and effectively a black box that's going to do something to the input image to produce the output image. Now, this is really just one canonical description of this problem. You may have a bunch of images going in the input and a single image coming out, or you might have a low-resolution input and a high-resolution output coming out, or a variety of different things. But this is sort of the core principle. Let's just say we have one image going in and one image coming out. And what we're going to do is to think about the filter, this black box, as a mapping from the pixels in the input to the pixels in the output. And this mapping is going to take several pixels from the input and somehow compute an aggregate of these and produce one of the pixels in the output. And we're going to do this for all the pixels. So this function f is the mapping that these arrows are indicating from the input to the output pixels. And it can be a different mapping, in fact, for each output pixel. And this would be the definition of a filter that is varying in space. And it could, in fact, be nonlinear. So we can write the same description for every output pixel. And we're going to have something like this, right? So each output pixel denoted by z here is some function of a bunch of input pixels. Now, very generally speaking, these input pixels can be in a small neighborhood, or it can be the entire image. This description is very, very general. Now, I haven't really helped myself here by writing things this way yet in terms of designing a filter, because this description is so general that it really doesn't help me with a design problem. I don't have a parameter space defined here for the design of this black box. So what I'm going to do next is to bring a model or bring a mathematical framework to try to design the filters in a more systematic way. But before I go there, let me just mention that we've applied this kind of thinking to the design of many different algorithms. As I mentioned, things like denoising, sharpening, brightness tuning, HDR, fusion of images, demosaicing, and you name it, many, many. Okay, so what's the next step in this process? So what we're going to do is to think about this mapping from the input pixels to the output pixels as being defined by a very, very simple weighted least squares problem. Okay, so this equation that I've written down here is simply an optimization problem where the unknown is the output pixel value z sub j. The known data points are the y pixels, which are the input pixels. And let's say I've taken n of them. And I've computed the least squares. I'm writing the least squares cost with a slight twist, and that is the least squares cost includes in it a weight function, which I'm calling kij. And this weight function is indexed by both the input and the output pixels. And this weight function is usually some symmetric function. I'll talk in a little bit about how we might design the symmetric function. Okay, so this very simple weighted least squares problem is going to be written down many, many times. In fact, it's going to be written down as many times as you have pixels. right? It's going to be written down for each z sub j. And if we solve this for each z sub j, we're going to get a very simple result. The result is the following. The output pixel z hat j is simply a combination of a bunch of coefficients multiplied by the input pixel values that you see here. And in fact, these weights, wi sub j, are simply the weights of this weighted least squares normalized so that the weights in this sum add up to 1. Okay, and that's a perfectly straightforward description for your design. So if you want to design a filter, here's what you do. You write this down, you pick a kernel function, something like this, and you solve this pixel by pixel, and there's your filter. Okay? Now, this framework turns out to have basically a descriptive power that explains many, many filters that most of you have used and that we've developed in the literature. So let me show you some examples. So suppose that I wanted to choose this kernel function so that it would give high weight to pixels that are near the position of interest, where I'm doing my weighted least squares, and give small weight to pixels that are far away. So here's what I would do. I would think about the pixels in red here, and I would simply take their spatial distance into account. And I would write, let's say, a Gaussian with some smoothing factor, with some variance factor here. And this Gaussian would basically give high weights close to 1 to pixels that are near each other, where xi and xj are nearby. And the weight would drop off as you go away from that center pixel. Now, once you've done this, the next sort of intellectual step is, well, why should I just consider the spatial distance? Why don't I also consider the distance in terms of the difference between the gray values of the pixels? Okay? And I can do exactly the same thing that I just did here. I can choose another Gaussian of this sort, except that here the function is going to be a Gaussian in terms of yi minus yj, differences between the input pixels. And it turns out that if I simply multiply these by each other, I can get, oh, let's see, forwarding here. Okay, here we go. If I multiply these by each other, what I'm going to get is something like this. And essentially what I'm doing is, because the exponents multiplied give you the sum of, the exponentials multiplied give you the sum of the exponent, I'm just going to be measuring this Euclidean distance between the pixels in the plane of the spatial and pixel domain. And this is, in fact, the principle for both the bilateral filter and the non-local means filter. That's exactly what they are, in fact. It's not just the principle behind it. It is exactly these filters. The bilateral filter uses both this distance and that distance in precisely this form. And the non-local means essentially ignores the spatial distance and says, I don't care how far away pixels are in space. All I care about is how different they are or how similar they are in terms of their gray value. And that's what you get. And this by no means is the end of the story. You can choose all kinds of different ways to measure similarity or dissimilarity between pixels. So another method that we've used, this is something that one of my students came up with a number of years ago, and similar things have also been done. Instead of measuring this Euclidean distance, which is what the bilateral filter does, you can in fact measure or approximate the geodesic distance between two pixels. And that is sort of the shortest distance on the manifold of the image itself. If you thought of the image as a surface in 3D, the shortest distance between two pixels, you could use that as the distance. And this gives rise to a filter that we called LARC for locally adaptive regression kernels. So here's the equations if you were curious. So here's the bilateral filter. It uses the sample positions and the sample values. The non-local means basically gets rid of the position term. And the only difference in this part is that the bilateral filter measures the difference between the pixels pointwise, and the non-local means measures the differences patchwise. So it actually doesn't just look at a pixel, it looks at a context around the pixel. That's really the only difference. And then the LARC filter is also a quadratic exponentiated. But the quantity in here is an approximation of a geodesic distance, as I just mentioned. I won't go into the details. But the key point really is not so much these three filters, and many papers have been written on this subject. The point here that I'm trying to get across is that infinitely many other kernels are possible. All you really need is some basic properties to be satisfied. You need a symmetric kernel, and you're in business. And I like to joke that once you realize this, what you have is kind of a paper writing machine on your hands. Right? Just change the kernel, write a paper. Change the kernel, write another paper. And so here's one way to generalize. It turns out this is directly related to something that people know very well in machine learning. It's been used a great deal. And this is the notion of reproducing kernels. And you might be familiar, if you've done any machine learning, you might be familiar with the concept of reproducing kernel Hilbert spaces. And this is not terribly different than what I just described. The admissible kernels in this space are functions k, so like kij that I wrote. Here I've just written it more generally in terms of two arguments, t and s. As long as they're symmetric, non-negative valued, and if you construct a matrix from this function, like a gram matrix, which are just values of this function evaluated at ti and tj, if this matrix is symmetric and positive definite, you're in business. So you can design your own. And in fact, once you've designed a couple, you can then combine them in all sorts of ways. Like you can do a positive linear combination of the kernels, you can multiply them, you can exponentiate them, and so on. And those are also valid kernels. Okay? So this generates this very simple concept of a weighted least squares followed by, a choice of a kernel followed by weighted least squares gives you a very large class of filters that include many things that we're already familiar with. Okay, so let me show you some examples of how these things are different. Generally speaking, we compute these kernels densely. So we compute them everywhere. For every pixel, we compute a kernel. Here, what I've done is just for illustration purposes, I've computed these kernels to show you the similarity between the center pixel of a patch and the pixels nearby it. So in other words, I've shown you what these kernels look like in non-overlapping patches. So you can see the bilateral tends to get a little bit messy around places where there's a lot of detail. Non-local means there's a lot of smoothing, basically, of the bilateral kernel. And Lark sort of somehow sits in between. And in fact, as I said, so this was an example of local kernels. You could do this non-locally as well. You can look really far away and use the same function to measure these similarities or dissimilarities. So here's an example. For these 2 points, the blue point and the red point, this is what the weights would look like for all the pixels in this image as compared to those 2 pixels respectively. Okay? So now we're going to use these weights to do a lot of our image processing. And let's see how that works. So let me bring you back to this notion of the very general formulation where we have the output pixel is some quote-unquote linear combination of the input pixels. And when I put this in quotes, what I mean is that this looks like a linear equation, but in fact, these weights, W, depend on the data because we used, for example, the differences between the pixels. So this is a linear filter only in appearance, but it's really a nonlinear set of filters because the weights depend on the data Y. Okay, so how do we write this general formulation in a matrix form? Well, if I write this equation for every pixel Zj, what I have is basically a bunch of weights that correspond to a single pixel. I can write all of these weights, I can stack them into a row, and then I can stack these rows into a matrix. And now this matrix W basically captures the relationship completely between the input pixels and the output pixels. Okay, so Y is the input image scanned into a really giant vector, and Z hat is the output image, again, scanned in the same way into a giant vector. And the matrix W, which is data dependent in general, gives you what I call a global filter, a global description of the input-output for my black box. Does that make sense? Okay. So now if you choose to use a local version of this so that many of these weights are 0, then the matrix W is going to have a lot of zeros in it. It's going to be a sparse matrix. If you choose to compute the weights between every pixel and every other pixel, then the matrix W won't be sparse. It'll be dense. It'll have values everywhere. But the description is still perfectly valid. All right, so as far as implementation is concerned, the way we go about this, as I said, we sort of proceed in 2 steps. The first step is we take the input pixel, we compute the weights, this e to the minus whatever you want to put in the exponent. You've computed the weights, then you're going to apply the weights, okay? And this is how it works. Now, when it comes to problems like denoising, you might raise an objection that, well, you know, these weights on the input are going to be computed from noisy pixels. And you would be absolutely right to raise that objection. So typically, the way we do this is that we don't compute the weights directly on the signal that we're given when it's noisy. Instead, what we do is something we call pre-filtering, or computing a pilot estimate. We compute an estimate of z using some simple filter. Okay, something, it could even be a linear filter. Just apply a Gaussian. Okay, and then we compute the weights based on this. So the pre-filter is applied, the weights are computed, and then the weights are actually applied to the original image, not to this pre-filtered image. So from a practical point of view, this is how we proceed. So let me give you a few examples of what these things look like. So the image on the left-hand side is a digitally scanned 35 millimeter photo from 40 years ago, 50 years ago. And it contains noise that is not Gaussian. It certainly isn't uncorrelated. It's real noise. And so the image, that's the image on the left. The image on the right is a bilateral filtered version of this. So the noise has been reduced. The next one is this LARC filter that I mentioned to you that uses the geodesic distance. And the third one, this one is the BM3D filter, which, as probably many of you know, is sort of the state-of-the-art patch-based denoising algorithm. And these are all sort of principles based on the same principle. Okay, it turns out this framework that I just showed you also has a very nice interpretation in terms of graphs. So one of the things that you can do is to think about an image as a graph where you pick a node j and you index all the other nodes or all the other pixels with I, and you connect these nodes together with weights kij. So what you now have is a weighted graph. And that weighted graph, of course, gives rise to this matrix K. And the weights, remember, that we actually use for filtering are K divided by this normalization, which makes sure that the weights sum up to 1. And I can describe this normalization factor as a diagonal matrix, where the diagonals of this are simply the sum of each row of the matrix K. So let me go through it again. You compute the matrix K, you sum the rows, and you divide each row by that sum. That gives you the matrix W. And what I just showed you, what I just told you, is exactly embodied in this equation. W is equal to D inverse K, where D is a diagonal matrix that normalizes the weights, and K is your original weights that you used for the weighted least squares problem. And the key thing is that the matrix W here has rows that sum up to 1. And another name for this is that it is a stochastic matrix, or it's a Markov matrix. So where does the graph interpretation come in? It turns out that if you take the matrix W and subtract identity from it, this is one of a few interpretations of what's called the graph Laplacian for this graph that I just constructed here. And if you've worked in computer vision or in machine learning, you know that the graph Laplacian has many, many uses, many interesting uses, including spectral clustering. You can use normalized cuts to do things like segmentation. So if you have an image like this, you can in fact use the structure of the graph embedded in this W to segment this image in two pieces. And now you can selectively apply your, let's say, denoising filter to the different segments. Right? So you don't need to really have a separate segmentation algorithm. Once you've got the matrix W, or equivalently the Laplacian, you've got what you need for doing segmentation and denoising at the same time. Okay, so this matrix W, it turns out, is a very special matrix. It has some very interesting properties. I've already mentioned the fact that it is row stochastic, meaning its rows sum up to 1. It turns out its eigenvalues also range between 0 and 1. It has a dominant left eigenvector, which is a constant. And what that means is that if you apply these filters to a given image, they preserve the average gray value of the pixels. And that's a good property for an image processing filter, unless you, for some reason, want to change the average gray value, in which case you can modify the matrix W. And there's various interesting things happen when you look at this matrix. Remember, because the eigenvalues are all between 0 and 1, if I keep raising W to higher and higher powers, that's equivalent to applying the filter multiple times. Now, all the eigenvalues that are less than 1, strictly less than 1, are going to collapse to 0, and a single eigenvalue is going to survive, and that's the one that is exactly equal to 0. So what ends up happening is that if you raise W to the kth power and k gets very large, you get a rank 1 matrix. And this turns out to have some nice mathematical consequences that I won't get into the details here. Now, you might be thinking at this point, this is great, it's very nice from a mathematical point of view, but it seems completely unrealistic to do image processing with these massive matrices. And you'd be right. So let's say I take a modest size image, this guy here, 480 by 640, and I looked at what the size of this matrix W would be. It would be about 300,000 by 300,000. Right? I mean, typical camera phone is now putting out 8, 10 megapixels, right? So that's ridiculous. How could you possibly operate with a matrix this size? Well, the truth is, what I've described here is a really nice framework for understanding how these filters work and for designing them. It is not intended to be a way of actually implementing things. And so the next things that I'll do in the remainder of the talk is to give you a little bit of an idea of how we go about some of these implementation issues. But before I do that, let me step back. I mentioned very briefly a few slides ago about using the filter W multiple times and raising it to a power. But you might also be wondering, what does it mean when I did this weighted least squares? I somehow came up with this nice description of all of these problems. But you might be thinking in the back of your head, what does this mean in terms of somehow a global cost function that I'm minimizing? I mean, we're using an algorithm that is based on a bunch of local operations, and it's based on a bunch of local optimizations. But it would be nice to understand what does it mean in terms of a global optimization problem. We can give that interpretation too, and that's what's here. So in order to do that, it's useful to think about this filter, these kinds of filters, as one step in an iterative process. So in order to do that, let me initialize my iterations z0 with the input image. And then let me consider this filter. So applying the filter one time would be the first iteration of this filter, right? And applying it multiple times, it turns out, is precisely what is known in the literature as diffusion. If you've read the many, many papers that are written about anisotropic diffusion and so on and so forth, they're nothing but this kind of operation with a particular kernel. The kernel of the sort that I talked about earlier. Okay, so if you have this as the operative iteration, now I can add and subtract zk to both sides of this, and I can think of this now as I gather these two terms together, and I put a little step size in front of this, and now this looks like a steepest descent iteration. Okay? And if you like, you can get rid of that step size and think about it as 1. So what this looks like, if you think of this as a steepest descent iteration, it says that zk plus 1 equals zk minus mu times the gradient of some function. So what is the gradient of this function? So if I have this, I've shown you that it's basically implying that you're using some kind of gradient that looks like this. If this is the gradient, then in order to get the actual function that we're iterating on, what you want to do is to integrate this expression. And integrating this expression is not very hard to do, except that it requires a slight technical detail, which is that the matrix W has to be symmetric. I'm going to brush that under the carpet right now and just tell you, if you look at this, what it tells you is that basically you have a sort of quadratic cost on Z. And the twist here is that the matrix W actually depends on the data. So if you do steepest descent on this quadratic cost function with a data-dependent W, you get exactly, as the first iteration, you get the filter that I proposed. And if you do more iterations, you get basically anisotropic diffusion. OK, so if I look at this as the thing that I'm trying to minimize, and I'm doing gradient descent on, in order to minimize this, you really need also a constraint, which is the energy in the function has to be fixed. Right? So really, it doesn't make sense to simply be minimizing that. You have to minimize it with the constraint of a fixed energy. And if you look at this, there's another way to write this, is simply to maximize Z transpose WZ divided by Z transpose Z. OK, this, it turns out, is called a Rayleigh quotient. The Rayleigh quotient gets minimized or maximized by the extreme eigenvalues of the matrix W. So another thing this shows you is that the result of the filter is basically the Z hat that you get. Another way to think about it, it's a linear combination of the top eigenvectors of W. I mean, in theory, it's a linear combination of all the eigenvectors of W. But in practice, you can compute the output by simply picking the top eigenvectors of W and doing this. So I've given you sort of 3 or 4 different interpretations of this. So here's what the eigenvectors look like. If you look at, if you look at this eigen-decomposition, so I've taken W and I've just written it as V transpose. V in its columns contains the eigenvectors. S is a diagonal matrix that contains the eigenvalues. And so I've taken a couple of patches here of this image, and I've shown you these are the first, here's the patches themselves, and here are some of the eigenvectors up to order 200, and these are the respective eigenvalues shown here. So you could do filtering on this image, for example. You could remove some very high-frequency noise-like things by just deleting this eigenvector and just retaining the top ones. And you could do many other kinds of filtering as well. So let me show you what happens if you choose different kernels. What happens to these eigenvectors? Let's say we choose a really brain-dead kind of kernel. Suppose we just use this Gaussian that actually doesn't even depend on the data. It turns out that the eigenvectors of the matrix you get, if you just use a Gaussian kernel, are functions that look like these. These are called Gauss-Hermite functions. They're basically polynomials modulated by Gaussians over a finite interval. And in 2D, they look like this as images. So if you just design a Gaussian filter and apply it to an image, what you're doing is the output image that you're producing is some linear combination of these very simple basis functions that don't depend on the data. So if that doesn't do it for you, if you don't get very exciting results, don't be surprised, because the basis that the choice of a Gaussian kernel implies is a very, very simple pedestrian basis. Now, what happens instead if we choose the non-local means kernel? This function here. This function depends on the data. And if you look at the eigenvectors of this, I've just shown you the eigenvectors for the luminance channel of this image. So the eigenvectors here are much more interesting. So the first eigenvector is a constant, so I'm not even bothering showing it. The second eigenvector is a very high contrast image, and the other ones basically fill in more and more details. And if you choose the bilateral kernel, you get something like this. It looks very similar to the ones before, except that you have some modulations of the brightness in these basis functions. Okay, here's another example of the eigenvectors just for illustrative purposes. There's the image, and these are 6 eigenvectors in increasing order. Okay, so let me kind of come back to this idea of functions of filters and doing iterations. So we already talked about this. We talked about how if you take this quadratic and you do steepest descent on it, you get this iteration. And you might wonder, is this the only kind of iteration possible? Obviously not. There are many, many types of iterations that you've seen in the literature. And let me mention a few. Bregman iterations. This is something that's been used for getting rid of staircasing artifacts in total variation minimization. So this was diffusion, as I said. This is a totally different iteration. And let me explain what it does. So this says instead of just applying the filter again and again, what you instead do is you update the estimate from the last iteration by applying the filter to the residuals from the previous iteration. So let's say, for instance, you're doing denoising. You apply your denoising filter, then you take the result, the denoised image, and you subtract it from the original noisy image. That's this residual. Then you apply the filter to that residual, and you add that back to the previous estimate. Now, why would you want to do this? It turns out this has a very nice property that it keeps your result from getting over-smoothed. If you look at this example here, for instance, this is just one iteration. If you pick a base filter, if you apply this filter to the residuals, you just rearrange the equations. What you see is that the output after one iteration is basically a combination of two things. There is a blurring operation, and then if you think of W times Y as a low-pass filter, 2I minus W is a high-pass filter. So it's a low-pass followed by a high-pass. So what this does is that it blurs, follows by sharpening. Each iteration is a blur followed by a sharpening, both steps being data dependent. And this might be useful if you, let's say you pick the filter not very carefully and you over-smooth the image and some of the details are lost, and those details are now sitting inside the residual. And what this does is it rescues those residuals and brings them back. And this iteration, it turns out, is simply doing steepest descent on this cost function. The previous one was just a quadratic on z. Here, it's a quadratic on y minus z. If you do steepest descent on this, you get precisely the expression that I talked about. And this has many different names. If you look in the machine learning literature, in the statistics literature, in the computer vision literature, regression boosting, Bregman iterations, and reaction diffusion equation, these are all various manifestations of this fairly simple idea. Okay, so we can do things like sharpening with this. Let's say I have an image like this, and what I would like to do is to sharpen it in a spatially adaptive way and add some structure to the image. You might do this in Photoshop. I'm not just talking about a simple linear unsharp mask, but something data dependent and more complex. So you can pick, for example, the bilateral filter and apply it to this image. Let's call the bilateral filter, in this case, W. If you apply some constant alpha times identity minus W times W, you get the output. So this is the input, and this is the output. Okay? So I've done nothing but apply a bilateral filter basically a couple of times. The second time being a slightly modified version of the bilateral filter, where the coefficients are just changed from W to alpha identity minus W. Okay, so this is kind of like an unsharp mask, but it's a very nonlinear unsharp mask, and it's based on the bilateral filter. And it doesn't have to be the bilateral filter. You can pick whatever filter you like in place of this W, as long as it's a smoothing filter. Okay, so the two things that I just talked about, the diffusion equation and the reaction diffusion equation, we can combine them as well. So here's the reaction diffusion equation, and here's the diffusion equation. I can combine them with two coefficients. Now you can start thinking about this. Everything that I talked about here didn't say anything about statistics. It didn't talk about Bayesian. It didn't talk about any prior information that you were using. But now you can start to think of it that way too. You can think of this as a data fidelity term. This term basically makes sure that the output image and the input image are close to each other, but not in your standard Euclidean metric. They are close to each other with respect to a metric induced by this matrix W. And then this one is a kind of regularization term, which uses the Laplacian of the filter that I defined earlier. And so for different values of the coefficient of this gamma, 1 to 0, you get either reaction diffusion, which is this extreme, or just diffusion, which is that extreme. And I can just rewrite this as I just mentioned to you. I can write it as the two pieces. The first one is kind of a data fidelity term, and the second one is your regularization term. You can actually think of this, if you like to think about this in Bayesian terms, in sort of the standard statistical terms. This first term is like a log likelihood function, except that it is an empirical log likelihood function because the function depends on something that was learned from the data itself, right? So it's a log likelihood learned on the data, and this is like an empirical log prior. In other words, a log prior, but it is also learned from the data. So there are interpretations between the sort of simple weighted least squares that I showed you and the more sophisticated and the more traditional Bayesian approaches as well. Okay, so again, this picture, I just want to emphasize that some of these things that we've done here can now be done in a fairly straightforward way with the eigenvalues. I don't literally have to take the matrix W, which is this huge thing, and raise it to a very large power. I can do it just on the eigenvalues. So you know, if you have a matrix that is symmetric and you have this eigendecomposition that I just showed you, VS, V transpose, then W raised to some power is simply V times S raised to that power times V transpose. So any function, any reasonable function of W can be implemented simply as a function of S. And that's what I'm saying here. So if you want to make a more complicated filter that isn't just W, but some function of W, you can apply that function, in fact, on the eigenvalues. So these two functions, t to the p and 1 minus t to the p, simply give you the diffusion and the reaction diffusion. The slightly cool thing here is that this p can actually be any positive real number. So you don't need to run the filter an integer number of times. If you run it twice, then p would be equal to 2. But here, you can set p to be any real number. OK, so as I said, we never use the matrix W explicitly. So exactly how do we do this in practice in a way that makes sense? It turns out the approximation that we use to the spectral components is using an old idea called the Nystrom extension. And the idea here is that you don't explicitly compute the matrix W, and you also don't explicitly compute the eigendecomposition of the matrix W. Instead, what you do is the following. You compute only a few rows of the matrix W. This is the key idea. You compute a few rows of the matrix W, and it turns out because W has very low numerical rank, you can compute the dominant eigenvectors of the matrix simply by scanning a few rows of W. I mean, this has some connections to compressed sensing ideas and to matrix completion problems and so on, which I'm not going to get into, but this turns out to be the key to making this happen. If you do that, then it turns out what you have is a filter that can be implemented in very low dimensions. So if your image is a very long vector, you're going to estimate a few of the eigenvectors, and those are going to be sitting in this long matrix. And then you're going to manipulate a very small number of eigenvalues, and then you're going to remultiply by the eigenvectors, and that's your filter. This VSV transpose can be decomposed in this low-dimensional space using the Nystrom approximation, which works like this. Again, to reiterate. Instead of starting with the input image, computing a complete matrix W, and then from that computing the eigenvectors, and then doing a low-rank approximation, what we instead do is we scan the image at a very, very small number of points. And when I say very small, I mean less than 1% of the pixels. And we compute the weights corresponding to those very few pixels. That corresponds to basically computing a very small number of rows of the matrix W. And then from this, we can go to the eigenvectors directly. I can give you a little bit more detail about how this works. So here are the steps. You compute a few rows of the matrix K. You rescan them so that they sit on top. It's just the permutation of the matrix. Because the matrix K is also symmetric, you now have not only a few of the rows, you also have a few of the columns. So basically what you have is this little blue strip of this matrix, and everything else in here is missing. Okay? And how does this define the entire matrix? Let me give things names. This corner, let me call it K1. This column piece, let me call it K21. And then the corresponding row piece will be K21 transpose. The Nystrom approximation is a fairly straightforward idea, and it says that matrices that satisfy certain regularity conditions can be approximated by K21, K1 inverse, K21 transpose. Okay, so this enormous matrix can be very accurately approximated by just knowing a few of its rows and a few of its columns. And this inverse here might worry you, but this is a very small inverse. Right? This matrix might be 1,000,000 by 1,000,000, but this inverse may be 50 by 50. Okay, so it's entirely practical to do this. And now if you want to compute the eigenvectors of K, if you use an iterative method, for example, you're going to be multiplying K by vectors a lot. And that can be a huge thing if you have to keep K in memory. But you don't have to keep K in memory. Because if you want to multiply K by V, you can write it this way. And if you look, inside each parenthesis, there's only a very small operation happening. Because K21 transpose is just a long vector multiplied by, a long matrix multiplied by a vector. This is a small inverse, and there's another long multiplication. You never have to hold the entire matrix K in memory. Okay, so just to kind of pop up and give you a little bit of the intuition back, basically you take the image, you compute these eigenvectors from it, you project the image onto this basis, then you apply some function of the eigenvalues, and then you reproject onto this basis and recombine to get the output pixels. And that's really all there is to it. There is another multi-scale way of thinking about this, which is that you can apply the filter multiple times, and each time look at the differences between the input and the output. And now what you have is you have sort of a coarse version of the image you're carrying through, and then you're also carrying through a bunch of details which you're going to manipulate and recombine to give you the output image. Okay, so as I said, there's many applications of this that are enabled, so let me just show you a few. You can take an image like this, and again, choose something like the bilateral filter, and apply it, let's say, 5 times, and you can get things that look like this. And these are basically a posterization effect that you can get. You can, as I said, this matrix W also has segmentation information in it. So let's say I have an image like this, and what I would like to do is to make the part of the image, which is the wall or the stone pieces, I want to enhance those, I want to sharpen those, but I don't want to touch the sky at all. The sky looks fine. Okay, so what I'm going to do from this image, I'm going to edit a part of this, and I'm going to let that edit propagate to the rest of the image. And the matrix W is going to make sure that that edit does not propagate beyond the right boundaries. It's going to give me a mask like this. This is a propagation mask implicitly coming out of the same matrix. And now I can I can propagate that edit so that all of these regions are sharpened, but the part of the sky up there is not touched at all. This is not really a two-step process, it's all in one shot. Okay, the same matrix, manipulating the same matrix gives me this. Okay, so there's the comparison between the original and the edited version. I can also do things like recoloring. Again, the segmentation information is very handy. I can give the user the power to go in and put a stroke here somewhere that says, hey, I want things like this to be changed to a blue color. And I can propagate that information to recolor the image pretty conveniently. Okay, so this sort of wraps up what I had to say. There is a bunch of things that we've written about this. If you're interested in some papers, these are sort of the main ones. The one on top here is probably the closest to the high-level exposition that I've given, and the other ones contain some more of the details. And you can find all of these papers at my website. And that's it. Thanks for your attention.